Well, again, today we're going to be talking about ESD. You may remember this meter from a previous video. This is my UT181A, and you may remember when I first purchased this, I had subjected it to a single pulse off of this grill starter and damaged the meter. Obviously, I've since then repaired it, but I had a lot of people ask about the grill starter and the voltages that this put out. So I did a segment where I talked about ESD, what this grill starter really put out, and how that compared with the IEC standards. I also talked a little bit about how I made these measurements, and that was with this small target. This target is basically a 2 ohm resistor, and it's followed by 26 dB of attenuation, and then this is just a section of RG400, and then this goes back to my oscilloscope. You can see our scope is set at 20 millivolts per division, and it's also 20 nanoseconds per division. And this is the transient caused by me touching this probe tip when I first sat down. So that 20 millivolts, that equates to roughly 200 milliamps per division. So that's how much current is flowing through that 2 ohm shunt right now. You can see it's a very fast transient. Typically our house is quite dry, and this wasn't much of a poke. I hardly felt it actually when I sat down. And unfortunately with some of these meters, especially from UNI-T, I find that they're very sensitive to ESD. But again, if you purchase a meter like this Brymen, and this thing has been tested, certified to pass the EMC standards, this meter is going to be tested to something much more severe than this little grill starter. So I've looked at buying a used ESD gun in the past. They usually sell for quite a high amount, if you can even find them. And then you'd have to find one that actually meets the current standards. So I thought I'd try to take a look at building my own. So that's what I'd like to show you during this video. So this is my attempt at making a homemade ESD gun. You can see on the front we have a reference. This is the ground. This is the pulse output. And then I have a DC output here as well. I have a small LCD which displays the output voltage in kilovolts. And it has a 24 volt in, as this potentiometer to set the output voltage, and a button to trigger it. Last time I had ran the piezo grill starter, I captured this waveform. You can see our scope was set to 100 millivolts per division. This equates to 1 amp per division, and you can see it's basically a 1 amp peak pulse. This is 5 nanoseconds per division. So you can see the majority of the energy was dissipated in about 5 nanoseconds. These waveforms were taken with the 64XI. You can see the scope was set for 200 picoseconds per division, and the scope is calculating a rise time of slightly under 840 picoseconds. And you can see there's 4 plots that are overlaid on top of each other. And those 4 plots represent 4 different pulses, and you get an idea of how repeatable this new gun is. And the red trace is zoomed out looking at the overall profile. You may remember when I talked about the 61326 standard, that calls for a 4 kV peak at 15 amps. And then they measure it at 30 nanoseconds out, and they're requiring 8 amps. And at 60 nanoseconds out, they're looking at 4 amps peak. You can see here that we're putting out 5 divisions, or roughly 10 amps peak. This is currently 10 nanoseconds per division, so 3 divisions out are 30 nanoseconds. We are about 2.5 divisions up, which equates to about 7 amps, and then 60 nanoseconds out, we're about 1.5 divisions up, or about 3 amps. So this waveform is a little lacking from the IEC standard. This is probably going to be acceptable. I just wanted to replicate the IEC standards a little closer than what the grill starter could do. So this is looking at the same waveform, just with my faster LaCroix scope. And you can see now, rather than 5 division, the peak actually is going up to about 5.5 divisions, or roughly 11 amps. And the reason for that is just the bandwidth of the scope is quite a bit higher, so that gives us a better picture of what's really going on at this high-speed peak. You can see the scope is calculating roughly 407 picoseconds off of this waveform. And if we zoom in, this is 100 picoseconds per division. And again, you can see the scope is calculating a rise time of roughly 400 picoseconds. So you can see if I plug it in, Display comes on. This has got reverse polarity protection in case you screw something up. One of the things I should mention is there's a lot of variance between these types of grill starters. You would think that these would output roughly the same energy levels, but this one on the right actually puts out quite a bit more energy. So if you're going to try to use a grill starter like this for testing ESD, you just want to have a way to characterize it to kind of get a feel for what the thing is putting out. You may remember this box. This is a small divide by 10 attenuator that I'd made. So if I put 100 volts into this, the output is going to supply 10 volts. And it doesn't matter the polarity of this. I show a plus and minus, but there really is no ground per se of this box. And it's also unidirectional this way. There is no input and output. If you're interested in seeing how this attenuator was made, I did a video on that. You can see the attenuator is attached to the DC output of our gun, and then our meter is attached to the output of our attenuator. So currently, you can see we're putting out 260 volts or 0.26 kilovolts, and our meter is reading 26 volts. Multiply that by 10, or 260 volts. So here we can see 1.23 kilovolts or 1.24. This meter is not real accurate. It's just there to give me a ballpark figure of kind of what the gun is set for. So you can see our UNI-T is reading roughly 594 volts. Multiply that by 10, or roughly 6,000 volts. So you can see if I plug these into these test leads here, so even with 500 volts, you can see it's not doing a whole lot. I could put my finger across this. See, and I can't even feel that. So even though the front end of this is seeing 6,000 volts, the output of this is pretty safe to handle. And again, this isn't made with little quarter-watt resistors. This has got some very large KDAC parts in there. It also has some Teflon spacers, and it's potted. And it also has some HRC fuses in it. Okay, so I have these two leads attached to the output of our ESD gun. And what I'm going to do is turn up the voltage. So again, you can see we're putting out roughly 6,000 volts. So you can see as I bring the leads together, get a little bit of an arc off of this. This isn't something you'd want to grab a hold of. There's not a lot of capacitance on the output, so I don't think that this would be lethal, but yeah, it'd definitely give you a pretty good poke. So again, this little grill starter, when I measured it, it'll put out about 15,000 volts. And, you know, is that lethal? Well, you can see it across my fingers. And, you know, I'm not dying. I can actually take it right across my heart. There you go. You know, and again, I'm not going to die from that. There's just not enough energy there. The pulse is very short. What happens if we put our fingers across this? So we'll go ahead and increase our voltage here. You can see this is now set for 6,000 volts. I've got my fingers right across the two probes, and I'm going to push the trigger button. And 3, 2, 1. Let's see it again. You can see my finger doesn't even twitch. Again, my own feeling about the two, this is pretty weak compared to what this is putting out. But again, certainly not lethal. So I did a little bit of research out on the internet to try to find some test reports where they showed the actual test setups for multimeters. And unfortunately, there really isn't a whole lot available. The test reports I did find, most of them just would say that the meter passed whatever test that they ran. And that was really the extent of it. I did find a report though from Intertech, and they were basically following the standard IEC guidelines. So they have a table, and the table has a ground plane, horizontal ground plane, and then they have that ground plane attached down to the floor through like their 400k ohm resistor, and the gun strapped into the floor, and they've got this thing sitting up on their insulator, and they're taking their gun, you know, and they're moving it around the meter, but they never tested it with the probes, which to me seems kind of senseless, because, you know, the meter gets shipped with these probes, and what's going to end up happening is the meter is going to be hooked up, and it's very conceivable that one of these could be attached to your ground of your equipment, which would go back to the earth ground, and you may come up and touch this thing without having any kind of ESD protection. So that transient could go right into the meter. So I don't necessarily agree with how some of these meters are being tested. So a friend of mine had bought one of those X-Tech EX540 or some meters, and he gave me his old meter. You can see it's kind of interesting. It has a Vicor across here. If you're not aware, Vicor is a power supply manufacturer, and this meter is basically what Harbor Freight sells. I've had this meter apart. There's basically no protection on this, and these meters I know can't survive any kind of ESD hit. So if this gun were, for example, hooked up to nothing and I'm zapping around this meter, I mean, what do you think's going to happen here? It's certainly not going to hurt it. But that's kind of what they were doing in that one test report. Now I know if I zap this meter directly across these leads, this meter is going to be damaged. So I've got this cable that I'd made for the bigger transient generator. I don't use it anymore, but the idea is that we could plug this into our generator like so. We just have our common output going to our black, and the pulsed output going to the red, and then we could attach these leads directly to our meter. So I thought for fun what we could do is take this meter. The case of this is actually at ground, and I'm going to turn up the voltage of this. I'm going to take our test lead, and we're going to attach that to the voltage input, and let's just give this thing a transient with only one lead attached and see if it damages the meter. You can see it's not even reading. A little bit of movement on the display. So again, we'll just attach this to our test box. This will be roughly 5 volts. You can see that's fine. And that looks fine. That looks good. Let's try it in resistance. So a 1 meg resistor. Dead on. This will be 100k. Looks good. And a 20k. And a 1k. And a 100 ohm. And here's your diode check mode. Here's with a single diode. So yeah, the meter appears to be fine. Now again, if I connected this transient generator straight across this, I would pretty much guarantee you this meter is going to fail. Again, I've had this apart. It looks a little bit better built than the ones that I see coming out of Harbor Freight now, but it's along the same lines. So this is my UT90A. This is made by Unitrend. This meter gets no love around here. Its sole purpose in life is to get damaged. And the last time I had it out, it went for a little swim. So it should just power up just fine. Yep. I'll just show you it still works. This will be a 1K ohm resistor. Of course, this meter is manual ranging. This will be a 20K and a 100K and a 1 meg. And this will be a 10 meg. Takes this thing a long time to settle, but it's still fairly accurate when you consider all that this meter's been through. That's pretty impressive. So this meter has actually survived this grill starter testing without any problems. Let's just see how it handles this new transient generator. We won't do a real extensive test on it, but we should at least get an over voltage here. No problem. Let's try on the 20 volt scale. Looks good. 200 volts. Looks fine. And 1000. Looks good. And a 50 ohm resistor. And a 1K and a 20K and a 100K and a 1 meg and a 10 meg. Let's try it in diode check mode. So this is a short. And this is a single diode, and here's 2 diodes. Let's try it with 3. Looks fine. Yeah, so if I squeeze the case together, so yeah, still fine. This is a UT181A, also made by UNI-T. This meter's had a lot of modifications to make it more robust. It's also very temperature stable, and it's got this backlight feature. You can see it lighting up here as I kind of cover up the sensor. So let's just see if this meter can survive this same transient after my modifications. Again, this gun is pretty close to the IEC standards. Certainly a lot closer than what this little thing was, but let's just see what happens here. Oh, you see the bar graph jump. So it's definitely picking it up. Rails it. Now really, I should be running both positive and negative transients. This gun recharges basically instantaneous, so by the time I can push the button again, this thing will be all ready to refire. There is some information in the standards about how fast you're supposed to hit these. Of course, you know, the standards would call out the ground planes and everything as well, which we aren't really following. My goal is really to see if the meters are robust. If they can handle this transient, they can definitely survive the IEC standards. So again, let's just have a look in the DC volt. And there's your 5 volts. And I have an easy way here to generate AC right now. But let's try it in the ohms mode. Of course, this would normally read a dead short if it were leaking. So there's your 10 meg. I think this meter could actually read 100 meg. Oops. Yeah, it's pretty impressive. That's a 100 mega ohm resistor. And I'm sure it's not going to have any trouble. There's a 50. And let's put it in diode check mode. Again, here's a short. No problems. Then this is with a single diode. And 2 and 3. Yeah, I didn't. Oh yeah, it does read 3. I think this was one of the quirks with this meter. After I modified it, we actually picked up the 3rd diode, but I think originally from the factory it couldn't make that reading. This will be in capacitance mode. Then we'll clear that out, and this will be a 150 picofarads. Close enough. Take it out of rel mode, and this will be a 0.1 microfarad. Yep, very good. So yeah, it doesn't appear that we've damaged this at all. I'll go ahead and refunctional test these later, but normally what you'll see is they'll definitely leak like in resistance mode. So yeah, my mods to the meter can survive this transient generator as well. So what about our UT181? Again, I damaged that meter with a single hit off of this grill starter. I had to go in and repair it, and then I basically chopped up the circuit board and I rerouted quite a bit of it, and I was able to correct the problems with it. So this meter now is very robust. It took basically everything I threw at it and didn't have any troubles at all. But let's just see how it does with our new static discharge gun. I don't know if we can make a pulse out of this just by manually tapping the meter. Yeah, okay, there's your frequency. And let's try diode check. So here's a single diode, looks good. Here's a couple of them. Let's just try it in capacitance mode. So we'll go to nanofarads, menu, and rel. And this will be 150 picofarads. Pretty much dead on. Let's try it with a 1 nanofarad. Looks good. And a 0.1 microfarad to take it out of rel mode. Looks good. There's resistance. Let's just try a 50 ohm. Looks fine. Here's a 10 meg. Looks good. Here's a 100 meg. And let's try a 1000 meg. That looks good. So here was our continuity test. It's a dead short. Obviously it's picking up something. We can check temperature. Let's try that. Should read about 20. Yeah, looks good. And DC volt. Of course, this is our 5-volt signal. Yeah, it looks fine. Again, I'll check the AC and stuff later, but I don't see any problems with the meter. But again, I basically redesigned the whole front end of this thing in the layout, so I'm not expecting this meter would have any problems with this testing. So I bought this little Techpower TP7050. This is actually made by KTI. It's a KT7050. Compared to the first analog meter I tested, this is not really bad. It's all surface mount on the inside. I was going to originally transient test this meter, and the problem is they share the current input with the standard input, and there's a fuse in line with this, and that fuse is shared for all modes, not just current. This thing actually has a couple of MOVs in it, so it's going to try to clamp that voltage. So if I hit this thing with a transient off of our generator over here, it's probably going to pop that little fuse, and so then I'm going to end up having to keep replacing fuses. So that's the reason I never ran this thing. Let's just see what this thing does with this static discharge. I don't expect anything, but let's just see what happens here. Somebody wrote me once about a Simpson meter being able to detect nanosecond wide pulses, and you can see here that meter will deflect even on this thing just a little bit. So yeah, I guess this meter can detect nanosecond pulses. I don't hear anything breaking down or anything in it. Yeah, I'm saying no effect on this thing at all. There's no sensitive ICs on the front end of these, so yeah, see, I never put the batteries in it, but we should be able to read DC volts with it just fine. So here's your 5 volt. This should rail it at 2.5. Yep. So 250. Yeah, it's fine. So Dave at EV Blog has been posting about a new meter that they've been working on with another company, and that meter is going to be an exclusive for him. So I'm hoping to get my hands on one when they're available, and I'll run these same tests on it. Of course, we don't have it available yet, but let's just try it with his rebranded Brymen meter. So of course, this meter, again, very robust. If you watch my review on it, I put this meter through some pretty big transients, and it had no trouble with them at all. You can see it picks it up. I don't expect this is going to fail. Again, Brymen will certify these meters to pass those EMC standards. We can flip it around. Again, I'm not expecting any problems with this. So again, this will be 5 volts. And no problems. continuity mode. There you go. Again, this will be 10 meg. And let's just try 50. And you can see it's definitely picking up a signal. That's going to be fine. Same thing, we'll short it out. Yeah, that's fine. And temperature. Yeah, that looks fine. And capacitance. This will be a 1 nanofarad. Looks good. Here's a 0.1 microfarad. That's fine. Diode check. Here's your short. Let's try it with 3 diodes. Yeah, no problem. Again, Brymen had this meter certified, so I'm not expecting any problems out of this. We'll hope Dave's new meter can survive these same tests. So I was going to make that the end of the video, but I feel kind of bad. We haven't blown anything up. It's like we didn't do our job. So you may remember another YouTuber had posted where they were using this fly swatter to test some of these meters. And this thing will put out quite a little bit of zap. And I had actually ran the UT90 across it, and I couldn't damage the meter with this. So I ended up putting like a 100 picofarad cap in parallel with this, and then I discharged that into the meter, and then eventually I just hooked this thing up to my half cycle line simulator, and I blew the whole front end out of this thing. That was pretty spectacular. So again, this thing will put out a DC voltage. Let's just put this thing in 1000 volt mode, and let's just see if this power supply can damage the meter. Let's bring this up a little closer. So I'm just going to go ahead and increase the voltage, and let's just see if this will damage this UT90. So there's 400 volts. There's 700. You're breaking down. Wow. That's 2000 volts right there. If you can hear that thing just sizzling. It's drawing enough current I can't do anything more with it. That's pretty impressive. Well, the UT90A lives to fight another day. Sorry I didn't blow anything up. I think that's going to be it for this video. So in the future, if you're one of the people that complained about me blowing up your meter with this little grill starter, get ready for this thing. Later.